Good afternoon, this is Schweitzer. We're going to run a little video here on how do you do a Bohr diagrams. This is after Niels Bohr. He created this little model, and it uses what's called the principal quantum number only. The principal quantum number is a part of quantum mechanics. It is symbolized with the letter N, and N stands for energy levels, which is this guy right there. It's going to be given a number 1, 2, 3, 4, and this just keeps going on. And it's just literally, you have the nucleus in the middle, and you have energy levels around the outside, and we call these energy levels, well, they're energy levels, and they are how we're given a number. So sometimes you'll see it like this. This is N equals 1, N equals 2, N equals 3. All right, so we have these electrons. Niels Bohr kind of made this like planets around the sun type situation. Okay, so many people know that the first energy level has 2 electrons, the second energy level has 8, third level has 18, fourth level has 32, and the rest of them you can Google or whatever, but this is something that maybe is commonly taught and less commonly taught nowadays in middle schools. All right, so an energy level contains a certain energy of electron, and then when that's full, it goes to the next level. Energy actually increases in this direction. Increases. Okay, so number of electrons, energy level. So we just listed that out right here. All right, so let's create a couple Bohr diagrams. How does this work? Well, just simply like, let's say hydrogen. Okay, now hydrogen. Now we call this what is called the ground state. Ground state. Now a ground state electron is just like it's in the lowest energy possible. So we have a nucleus, we have our first energy level, and we have an electron. The electron could be simply like a letter E, like that. That's it. If we were to do, let's say, helium, okay? Now, helium, again, we always assume ground state. I'll show you an example I mean by an excited state in a moment, but helium would be just like this. Now, again, this first energy level can hold 2 electrons. So helium has 2 protons, like this, and we would have just two electrons like this. Now, it doesn't matter really where you draw them on here. There are common things. People put them in pairs, but technically they just got to be in the energy level. The Bohr diagram is not super precise and accurate to what's actually happening in the atom. There are no actual orbit-like things like this. The best thing about this is that it has electrons quantity in regions that represent energy levels. But there are orbitals and different shapes of things. So this planet thing zipping around like this really is not real true. So how you place the electrons in here technically wouldn't matter. Okay, so let's do another one. Let's say beryllium. Now beryllium, Be, this one's got 4 electrons, 4 protons, and it's got neutrons. Now the neutrons can be listed as a circle. We don't know how many, they vary based on atoms. So 4 protons, let's say it's neutral, so it's got 4 electrons. So as you get moving along here, you might want to just list as 4p, okay? And the number of circles could be listed as well for neutrons. And they might just do a dash like this, 1, 2. Now the energy level is full, so we have to do two more. But this one's going to go in the second energy level. And again, I could put 1 here, and we typically put them together, which we'll see more about later, but like that, okay? This would be beryllium, okay? Let's try another one. Let's say, I don't know, let's do oxygen, okay? Oxygen has 8 protons, and it has, if it's neutral, 8 electrons. So I got my 8 protons. Its most common isotope is 16 of mass, so that would be 8 neutrons. And This, let's just say, is our first energy level, n equals 1, and it's got 2 electrons in it. Second energy level, all right, needs to get 6 more in there. The second one can hold 8, so that can hold a maximum of 10 in this guy, so I'm still good here. I can have 1, 2, 3, 4, so 2, 4, 6, 7, 8. I'll draw like that. We'll see more, I guess, in later videos. But this is oxygen, okay? Oxygen. Right, that is check creating Bohr diagrams. Now what about ions, okay? All right, well, let's take a look at an ion here. Let's say if we were to do, let's say, oxide, which is O negative 2, okay? Now there's a couple things we're looking here. Is that O negative 2 is a very common, this is what we call a common ion. And oxygen's always -2. People figured this out pretty quick, pretty early on. So what does that look like? Well, we have our 8 protons. We have our neutrons in there as well. And rather than having only 8 protons, 8 and 8 electrons, I added 2 electrons. So it was, what happened here is the oxygen atom gained 2 electrons to form O negative 2. So what happens here is we have 8 protons, we have 8 electrons, I added 2 more, so this is a before snapshot, this is an after snapshot. So now I have 8 protons still, but I have 10 electrons, alright? So the both sides are equal, there's 10 electrons on the left side, 10 on the right side. We have a fancy name for this, which we call reduction. Right, reduction. Anyway, so let's draw this out. I might give myself a little bit more room here. So I have 8 protons. Let's just say I have my same 8 neutrons. And first energy level, second energy level, okay? I have 10 electrons. That means my second energy level is maxed out. I have 2 from my first energy level, 8 for my second, which is 10. Alright, so scientists quickly figured out that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So scientists kind of caught the whiff of what they're seeing in nature is that full shells tend to be more stable. So this is no different here. This is an ion. I got 8 protons, 10 electrons, so this is an anion of oxygen, which is O negative 2. We tend to call this full shell thing the octet rule. But it really is just a generalization that a full shell tends to seem to be more stable. Alright, so that is one thing we want to kind of look at is, okay, with Bohr diagrams, what can we do? Well, on the periodic table, you might note that the very end of the periodic table is the noble gases, and these guys have a full shell. So atoms are consistently, we'll use Bohr diagrams to show this. Bohr diagrams is just a tool to show how atoms work. So electrons are being gained, like oxygen did, to form O minus 2. Now, O minus 2 is what we call isoelectric with neon. They both have 10 electrons, and they both have the same looking Bohr diagram. So the exact same Bohr diagram, only difference is the number of protons. So they have 2 electrons. They have 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's neon. Okay, and it's the number of protons that really varies here. This could be oxide. It could be neon. It also could be, this is oxygen. It could be fluorine. What about F negative 1? Okay, F negative normally had 9 electrons, it gained 1, bumped it to 10. And even on the other end of the periodic table, you should note that we have things like, let's look at the periodic table for a second here. So neon's here, but these guys, sodium, magnesium, and aluminum, also are trying to get full shells. So let's take a moment and try this out. Okay, let's try sodium for example. Now sodium, Na, has 11 protons. Okay, so let's draw it out. So first energy level, 2. Second energy level. Now we're just using these Bohr diagrams as a tool to learn about how atoms operate. 1, 2, 3, 4, 5, 6, 7, 8. That's 10 electrons. So there's one more energy level here on sodium, and then this thing is going to be done. And you can put it anywhere you want. There you go. That's sodium. But of course, Na plus 1 loses this electron, and now it looks just like that guy. So the same thing happens for magnesium 2 plus or aluminum plus 3. For example, now these guys are all losing electrons. So when you lose, it would say aluminum goes to aluminum plus 3 plus the 3 electrons it just lost. So aluminum has 13 protons and it has 13 electrons. Now the aluminum ion has 13 protons but only 10 electrons, and there's the electrons that it lost. So 10 plus 3 is 13, there's 13 over here. We call this oxidation. And because these atoms are trying to get to a full shell, we have a common ion that atoms tend to form. So it's called a common ion. And we're going to end there for today. The most common ions here, we'll just mark them out, and we'll talk more about them later. But because of the number of valence electrons these atoms have and how they gain them, this guy has 1 valence electron, 2 valence electrons, 3, 4, 5, 6, 7, 8. The charges these guys form, the teeter-totter point is right here, is going to be -3, -2, -1, 0, +3, +2, +1. And this guy teeter-totters on +4, -4. Alright, thank you very much.